Machine learning models now process the complex turbulence of the atmosphere in a fraction of the time required by traditional simulations. On short-term deterministic benchmarks, these architectures routinely outpace established numerical weather prediction models like ERAs. But the Earth's climate is shifting. Global warming is pushing the atmosphere out of its known distribution, shattering historical records. When faced with these novel, extreme conditions, the most highly praised AI models display severe structural blind spots. Success on a deterministic benchmark relies on pattern recognition within historical data. It is distinct from possessing a physical understanding of the atmosphere. This chart, based on findings from researchers Zhang and colleagues, tracks exactly how models handle anomalies. The x-axis measures the record exceedance margin, how far an event pushes past historical limits. The y-axis tracks forecast bias, or how badly the model misses the mark. Look at the traditional physics-based model, HRES. Even as the extremes become more severe, its error rate remains relatively stable and flat. Now look at the machine learning models, like GraphCast and Pangu. Their lines plummet. As heat, cold, and wind events break records, these models massively underestimate the intensity of the event, with the bias spiking and a near-linear trajectory. By synthesizing 4 recent research papers, we can map exactly where this machine learning pipeline breaks down. Current AI forecasts are tethered to the conditions of the past. As we move into an era of record-breaking events, that connection becomes a liability. This document snippet defines the legacy baseline AI is trying to replace, the standard approach. This method relies on large-scale determinism, or LSD, to constrain the basic features of the climate system. Look at equation 1. Physical laws are written in terms of large-scale variables. The small-scale processes, represented here by radiation and convection closures, are determined entirely by the larger state of the atmosphere. These closures act as parameterizations. They allow traditional models to account for diabatic heating, even when the actual physical drivers, like individual cloud formations, are too small to simulate directly. This scale separation approach works well for planetary trends, but as the Earth warms, accumulating regional discrepancies are challenging its validity. The mounting friction in these traditional methods is exactly what prompted the rapid push toward disruptive computational approaches, like machine learning. Recognizing the mathematical rigidity of the standard approach is essential. It tells us exactly what AI models are attempting to replace, and reveals exactly where they begin to lose their way. There is a common professional misconception that AI weather models are discovering new atmospheric patterns strictly by analyzing raw observation data. In reality, they train on reanalyses. These are massive historical data archives compiled over decades, and these reanalyses are actually created by running traditional, physics-based numerical models alongside those historical observations. Researchers Smith and Thorpe define this bounded archive as information set I, the absolute limit of all information available to a forecast. The machine learning model operates entirely inside this box. These operational ML models function as hybrid systems, tethered directly to legacy numerical methods. Because the AI trains purely on the outputs generated by physics-based models, it irreversibly inherits their archive limitations and structural blind spots. These AI models do capture subtle, short-term atmospheric dynamics with high accuracy, even without those mechanisms being explicitly coded into them. Yet, climate scientist Adam Scaife identifies a critical failure. AI architectures struggle to reproduce low-frequency variability and slow-moving climate shifts. Take the quasi-biennial oscillation, or QBO. It is a slow, multi-year climate rhythm driven by the gradual descent of equatorial winds through the tropical stratosphere. The root of the AI's failure here is mathematical. These models are optimized using a rolling 6-hour mean-squared error loss function. That short window creates a loss landscape that is blind to cumulative integration over months or years. The rapid 6-hour targets act as a filter that simply blurs out the slow-moving wave beneath. An AI meticulously trained to minimize error in the next 6 hours is mathematically penalized for attempting to understand the next 6 years. So, what happens computationally when this system encounters an extreme event completely outside its training distribution? To answer that, we have to look at the core capability of traditional models: extrapolation. Physics-based models use partial differential equations. Because the laws of mass and energy conservation are universal, these formulas allow the model to calculate previously unseen states and scale infinitely outward. The data-driven AI approach relies on interpolation. It moves between known historical data points, but hits a soft cap at the outer boundary of its training. Without physical equations to guide it past that boundary, an AI model simply dampens the extreme anomaly, pulling it back toward a known historical average. This interpolative soft cap explains the data from Zhang's study. It is the exact reason the AI systematically underestimated the extreme heat waves and wind speeds of 2020. The AI does not discover new physics during an extreme event. It averages out the anomaly simply because it lacks the mathematical permission to imagine a world hotter than its training data. AI weather forecasting delivers forecasts in seconds, maintaining high performance within historical norms. But it is held back by three structural anchors: reliance on legacy reanalysis, short-term loss functions, and purely interpolative architecture. As the race to build full AI climate emulators accelerates, will these systems inevitably inherit the extrapolation failures of their predecessors? Scaling up compute, adding billions of parameters, or feeding in more historical data will not solve a strictly mathematical boundary issue. Solving this requires alternative training regimes, architectures that move beyond pure data mining to explicitly enforce physical constraints and energy balances. To predict the novel realities of a rapidly warming Earth, the fundamental laws of physics cannot be omitted from the code. They have to remain in the driver's seat.